next presentation is the National Research Platform, Nautilus Kubernetes Cluster. The presenter is Mohammed Firas Sada, who will be presenting the aforementioned title. Mohammed is a researcher at the San Diego Supercomputer Center and the University of California, San Diego, specializing in high-performance computing, deep learning, and advanced networking. He traveled to us here today from Pittsburgh, Pennsylvania. Welcome, Mohammed.
Hello, everyone. Can everybody hear me? I'm just testing out the microphone, making sure everybody can hear me. Sorry, just do I switch stuff? Oh, perfect. All right, so welcome everybody. I'm just going to take a little bit of your time to talk about the National Research Platform and the Nautilus Kubernetes cluster, which aims to be an academic Kubernetes cluster that provides an open cyber infrastructure to academics, research groups, and educational institutes across the United States and internationally. So the National Research Platform, it started off as an idea called the Pacific Research Platform, or PRP for short, which was a project that started off in San Diego in California to sort of bridge the gap in having access to cyber infrastructure between smaller institutes that don't have access to these resources and can't afford providing these resources for themselves, and between larger scale institutes that do have these resources and have them to share. And the main motive here is bridging that gap to address the rising demand in having cyber infrastructure, which is something that we see today more and more, especially with the rise of AI, because access to AI is essentially access to hardware, and especially with moving towards the end of Moore's Law, we're heading towards a new era, an era of new targeted specialized hardware. So I'm a modern day scientist from whatever science domain needs that new specialized hardware to do their research work and to conduct their classroom education and so on. And with these targeted architectures, there is a barrier there. It's not an easy task for the science domain researcher to set up environments for those different hardwares and to adopt those specialized hardware devices, know how to configure them, know how to install them, and know how to use them, and how to adapt to them, how to have researchers that work with them, collaborators, students, so on, have them be able to use those targeted new novel architectures. Things like we have, like modern day, we have in every data center, and in the academic world, we have a whole bunch of PUs, so GPUs, CPUs, we have APUs, IPUs, TPUs. It's even getting hard to track all the PUs. Essentially, we have those novel architectures, those accelerating cards that are optimized to do generative AI work. And there's always the added risk of someone purchasing that hardware to do their work and not even knowing how to configure it, or to find out later that it needs some sort of proprietary software that they don't have access to. So that's where we come in. We come in to provide the infrastructure for those researchers, for those scientists, to have them ready in general availability with both the hardware and the software environments and the networking infrastructure that provides all of it, with the future outlook always focused on providing that advanced CI to everybody to bridge the gap in equity and to essentially ultimately just foster innovation and provide access to resources for education, which would drive that innovation and building and empowering talent. And where we're at now is that we have the National Research Platform, which is a collaboration between more than 70 institutes today. And those 70 institutes, we mean here in this context, so those are institutes that are contributing hardware to the cluster. And it's mainly led by researchers at the San Diego Supercomputer Center, at UCSD, and our partners at the University of Nebraska at Lincoln, and the Massachusetts Green High Performance Computing Center. And of course, it includes contributions from the National Science Foundation, the Department of Energy, Department of Defense, and many R&D institutes and organizations across the United States and in multiple continents. And the way all of it operates is under the umbrella of one Kubernetes cluster. So all resources, hardware and software, are provisioned through one Kubernetes cluster called Nautilus. And you can see here, so Nautilus provides to the research and education community various hardware resources, including a variety of GPU resources. Some of them are data center cards like the NVIDIA A10, A100. Some of them are marketed as gaming cards. We're talking about GTXs and RTXs, and different hardware resources like FPGAs, both AMD, Intel, and so on. And it's used by researchers from various science domains like life sciences, physical sciences, computer scientists, and so on and so forth, with the goal here to expand and scale as we go up. And if you go to dash.nrp.ai, you can see a near real-time dashboard of our resources. In comparison to hyperscalers, in comparison to your commercial data centers, our resources are somewhat moderate, but it is essentially a valuable resource to the academic community that we hope to expand and scale. Currently, we stand at more than 80 sites with more than 400 nodes. The present number between making those slides and presenting, we are at more than 425 nodes, at 1,400 GPUs, different CPU, more than 27,000 CPU cores, and various novel hardware architectures to provide to the scientific community. The cluster has been in operation for more than 6 years now, and it provides various file systems, storage options for users, including Ceph, the Ceph file system, the CERN VM file system, S3 storage, and various networking and monitoring tools like perf sonar, traceroute, and everything. I'll get to this more in detail later, but everything is monitored and exported in Prometheus in dashboards. And we provide all the software resources as well to be able to use these resources, between deploying JupyterHub for users, GitLab, and DevOps tools with CI/CD pipelines, and cloud storage software solutions like Nextcloud. And since it's academic, everything is open source, everything is free, we tend to focus on open source solutions with everything that we provide. For example, Jitsi is a video conferencing tool that we provide for the community. We have various edge hardware as well. So I'm just going to focus a little bit here on network resources. So the traditional model for a Kubernetes node that is integrated into Nautilus is that it has a ConnectX-6 network interface card, and most of them have two ports, sorry. So one port is what provides the connectivity to the commodity internet, to the backbone networks. That port is used for deployment purposes. The other port that is readily available for network researchers to create their own sort of sandboxed network environment, their own network that they can experiment in. With that, most of the switches that we provide are Tofino switches. Those are P4 capable. For those of you who don't know what P4 is, it's short for programming protocol independent packet processors. It's a C-style language that sits on network devices and allows users to develop packet processing pipelines independent of specific protocols. So you can define your own protocols the way you want. And Intel Tofino powered switches are capable of doing P4 programming, and that is one thing we provide the software environment for researchers to program. And we also provide Xilinx Alveo U55C FPGAs. Those FPGAs are, for those of you who don't know what FPGAs are, the easiest way to sort of oversimplify their definition is that they're fully programmable hardware, and the models that we provide also can act as P4 capable SmartNICs, so smart network interface cards, so edge devices that can add network programmability and are readily available to provision with Kubernetes. We provide different models of the FPGAs like the Bitware 520N MX FPGAs, the Alveo SN1000, and we're trying to add more and more DPUs like the NVIDIA Bluefield 2s. We have Bluefield 3s on the way, and smart computational storage like smart SSDs. We're trying to deploy more and more of that as the need for them scales up, especially with AI workloads, where you can have your storage components be also sitting on the edge of the network and have that sort of smart programmability to them, with the SSDs being programmed with embedded FPGAs to them. And for the network researchers, we provide on the cluster multiple tools like Multus, which is a container network interface plugin, and Calico, which is also another CNI. Both Multus and Calico allow users to conduct network experiments in their pods on Kubernetes. I'll get to that in detail a little bit more. And we provide access to ESNet Sense. So ESNet is the Energy Sciences Services, the Energy Services Network at the Department of Energy. They have written an orchestrator that allows users to provision L2 paths between Kubernetes nodes. And that is one service that we use to enable network research. Just gonna show you another idea of the hardware resources we're talking about here. We try to focus on variety over quantity. Like I said, we're sort of on a smaller scale, but we try to provide a variety of hardware. So you can see we have a large number of GPUs, different kinds of FPGAs. We have the Qualcomm Cloud AI 100 Ultra cards. Those are cards that are optimized for generative AI, and we're talking here, to put it in tangible terms, we're talking PyTorch transformer models. And we have x86 for 64 nodes, and we have ARM nodes. So the reason we're sharing this here today is to just shed the light on the sort of pain points that we face and how they're somewhat slightly different from hyperscalers, somewhat different from homogeneous systems and homogeneous data centers, and the sort of problems that we face and how we address them. So in dealing with the scientific community, we have a consistent need for bleeding edge hardware. Some of that hardware isn't designed in a way where it can interact with each other in a friendly manner, isn't designed in a way where it can be provisioned with Kubernetes in an easy way, and that leads to some collisions. One of them is firmware and driver health. So different hardware, different DPUs, FPGAs, so on and so forth. Some of them require, for example, custom kernels, and so the hardware comes with the custom kernel you're supposed to run on the actual host, on the actual node. But we have scenarios where we have multiple kinds of systems deployed on the same server, and that leads to collisions that somewhat, in some cases, requires us to go and apply patches to kernels, get the source code for the custom kernels they have, and sort of do our own debugging and getting to the part where we understand what's going on and addressing that. Another thing is that we're trying to get to every single campus in the United States and beyond the United States. With that, we have a Bring Your Own Resources initiative where different campuses, different institutes just join in their hardware. That adds challenges because basically hardware, the normal way it's added is behind what we call a science DMZ, or a science demilitarized zone, which means they get provided access with no firewalls, no blocked ports. And simply put, we add the resources with the limitations that we have. So not all nodes, for example, have the same bandwidth. Not all switches have the same specifications. Not all the switches are from the same vendor. We deal with a lot of homogeneity in the resources that we provide. And with that, we have different bandwidths across different links. And that, in many cases, needs to be addressed because researchers running workloads, yeah, for the most part, they care about memory, CPU, the GPU, the resources they're getting. But in many high demanding cases, users do care about the bandwidth they're getting, and it does affect their experiments that they're running. And that is one thing we address with node labeling and sort of advanced scheduling with Kubernetes, which is another incentive to use Kubernetes in data centers, where users can specify the bandwidth that they need for their pods. So a pod is a single instance in Kubernetes. It's capable of running of one or more containers. For those of you who are not familiar with Kubernetes, it's essentially a pod is the smallest instance of a container that you can run, for example. So in our context, you can say container as well. And we also have all the network components that are running on the servers, on the nodes, sort of overlapping in some scenarios. We have Calico, and Calico is what provides the connectivity between those Kubernetes nodes and provides the networks from the node to the pod. and essentially the Kubernetes topology that we're using. And we also provide Multus, and Multus is another CNI. And Multus, the incentive for us using it is that it allows users to attach network interfaces into pods. So as a provisioned resource. So if I request a network interface a network card interface, it is provisioned to my pod. And then the scheduler knows that it's taken and there's no collision. I can provision it as my own resource for my own experiments and run my experiments, which always is coupled with using the ESNet Sense orchestrator and allows us to do very specific per packet processing pipelines using P4. And that is also always one thing we have to address. So the network experiments running on our network don't collide with each other. And one simple scenario of that is that we have very high demanding research domains like energy physics, particle physics. In many cases, those science domains in their experiments, they require their own L2 isolated paths using VLANs. And one example of that is an experiment we did between CERN in Geneva and our nodes at UCSD. So we have NRP sites at CERN and we have NRP sites at UCSD. And we ran experiments where we had the whole data transfer pipeline between CERN and UCSD. Of course, that was ran on its own VLAN using the ESNet Sense and the ESNet Sense operator, which we wrote in-house to provide user accessibility to starting your own private, or by private I mean your own, dedicated to yourself, L2 paths, and provisioning them with Multus. And there's always also the pain point of provisioning through Kubernetes, because not everything is built for Kubernetes. Not all software systems are built to run inside pods, and not all hardware systems are built to be provisioned with Kubernetes, because we deploy a lot of hardware systems that do not have Kubernetes device plugins, and therefore the Kubernetes schedulers in different kinds, they don't see them as a provisionable resource. And we address that either by writing our own in-house device plugins and that are sort of tailored for the use case, or using VMs inside of Kubernetes with KubeVirt, which allows us to define any PCI device as its own resource that gets attached to one VM at a time as a dedicated resource, and therefore allowing us to escape the need to adding sort of privileged or very system-capable Kubernetes pods running on the cluster that can interfere with the sort of security, because privileged pods can do things on the host node. And that is always something that we don't want, because even though we're running in a scientific environment and part of the scientific process is having things break, that is something we want to avoid having on the nodes, on the host nodes, because we don't want to break our systems. And yeah, one of the science domains we try to service, and one kind of experiments we try to service is network experiments. And generally, the way of going about that is using the Sense orchestrator, which allows us to establish the L2 paths. And what it does is that it starts the VLAN interface on the host node. So whoever's using the orchestrator and the associated operator get their own VLAN interface on the host node. But to be able to access that, that's where Multus comes in, as we talked about. Multus allows us to define a resource called a network attachment definition, which allows us to specify what interface from the host node gets attached to my pod, to my container, where I can run my containerized, virtualized workloads, whether it's a VM or a pod even, and use that VLAN, use that dedicated L2 path with quality of service. And there I have my experiment pod, or like I said, VM, where I can run my workloads and do my network experiments. And of course, the National Research Platform is also part of a bigger topology called the AutoGOLE Sense topology, which, as you can guess by the name, is orchestrated by the ESNet orchestrator. Sorry. And as you can see, just to give you an idea of the AutoGOLE Sense topology, so it includes many R&E, many research national labs and research institutes and campuses across the United States on the ESNet backbone. ESNet is the Energy Services Network. It's part of the Department of Energy. As you can see on the top left corner, that is a topology of the sites they connect across the United States. For the sake of simplicity, every one of these maps is cropped only to fit the United States with, if I remember correctly, all of them including international sites. So NRP nodes are part of the ESNet backbone. More interestingly, they're also part of the Internet 2 backbone, which connects multiple, like we said, research institutes, multiple public institutes, and multiple campuses across the United States and internationally. And you can see on the top, on the bottom left corner, this is a federated testbed for network experiments called the Fabric testbed. It is also a sandboxed environment where network researchers can do experiments, and it has multiple sites as well. And NRP has connectivity using the orchestrator to that, where you can see the NRP sites on the top, on the bottom right side of the slide. And as you can see here, the overlap is very interesting. We have multiple campuses that include sites for both environments and multiple backbones. And that's what makes using the orchestrator more interesting. And ESNet Science it's short for software-defined network for end-to-end network science at exascale. And like I said, it allows us to provision L2 and L3 paths between any two endpoints on the topologies that we just showed in the slides earlier. And if you're interested in details on how it works, so it runs on the Kubernetes nodes in pods, and those pods are configured to connect to the switches. It's switch agnostic, so vendor agnostic, very whatever the vendor of the switch is, whatever OS the switch is running, it has configurations for all of that, so it can run on any or virtually any switch and any Kubernetes node. It can also run on bare metal to sort of add sites to the AutoGOLE Sense topology, which is an open initiative where folks and groups can actually add sites to it, and that makes them readily available on the orchestrator for the scientific community, for experimenters, and that incentivizes the need for us to write an in-house operator that allows users, in a simple YAML definition, start an L2 path between their pods. So they can either annotate it with a simple line in their YAML, and then their pod, their container, has a path from the site it's running on to another site on the National Research Platform, on the Nautilus cluster, where they can specify the bandwidth. And that is a quality of service bandwidth. It's never going to drop below that as long as they're provisioning it. And they can specify the VLAN tag that they're going to using, or have it set to auto, or it can be automatically determined. And they can, of course, check the custom resource, which is the sense path that they're using, and check what VLAN tag got assigned to them if one wasn't assigned already. And the way it works is that when you start with the sense operator, once you start the sense path, which is the name of the object, once you start it, it connects to the orchestrator, starts the L2 path, and then creates the Multus network attachment definition that we talked about. So creates the definition of how to attach that interface to the pod, and then you can start pods with it. If you annotated the pods as we have in the example, your pods will automatically have all of that predefined. Once the path is started and QoS is guaranteed, your pod gets patched with that interface on it. And therefore, your pod will see the interface. If you have two pods on two different sites, you'll see one interface here. You can see it with ifconfig, for example, and you can see the other interface here. And you don't have to need to know what's happening under the hood. You'll just have two interfaces at two different, even distant sites with QoS WAN. And one use case for that is the use of SmartNICs. So SmartNICs are like we said, one hardware resource that we provide, because they're network interface cards that provide programmability, whether they're FPGAs who are fully programmable with your own from scratch beyond L0 definition of what the network should be, and your own definition of the control plane in the P4 control plane, and whether through smart DPUs like the NVIDIA Bluefield line and other new architectures that are coming out every single day. And one use case for that is popular on the National Research Platform is, like we said, testbed integration. So Fabric is another ecosystem. It's sandboxed, so it's an area where network experimenters can go and actually break stuff without affecting the systems they're running on. And Fabric runs with virtual machines. The National Research Platform runs with Kubernetes. They're two different ecosystems, but they share multiple campus sites, and they're fully integratable, fully interoperable using the Sense orchestrator. And we also provide something called the ESNet SmartNIC stack tools. So the ESNet SmartNIC is a software project that provides the P4 programmability to the Xilinx Alveo FPGA line. So for those of you who are familiar with what FPGAs are, the U280 FPGAs, U55C, U200, U250, those FPGAs are part of the Open NIC shell, which provides P4 programmability. The ESNet SmartNIC tools provide all the command line tools that one would need in provisioning these cards, and between providing a DPDK driver and allowing users to start package on, and command line interface tools and probe counters and so on and so forth. So it's almost as practical as having your own sort of federated switch on the edge on every node that has FPGAs. And a brief example of that and how we used it in our own network research is FPGA P4 experiments. And this is a demonstration that we've shown on the National Research Platform, which is using those FPGAs for telemetry with SRv6. So segment routing is simply put, it's a technique that allows us to dictate what the packets, dictate how the packets are steered through the network, through the topology using the control plane, as opposed to relying on the routing tables. And there, let's say, every segment or at every hop, we can define how the network is steered from the packet definition. So for the example of SRv6, in our IPv6 packet definition, the segment list that the network is going to traverse is predefined in the packet definition, dictated by the control plane. And this is something that we demonstrated with the FPGAs, because FPGAs, they're capable of doing timestamping to the order of nanoseconds, which is more accurate than using NTP with switches. And we have FPGAs at multiple sites, and it's something that is shared between the Fabric testbed and the Nautilus cluster. And we've ran our segment routing experiment, where at every segment or every stop that we have at an FPGA site, we injected our timestamp into the SRv6 definition. So regular SRv6, it uses 128-bit fields for the segments at every segment. We modified that logic to use 64 bits for the segment, the ID, and the other 64 bits for the timestamp at every single site. And we, of course, did that with P4, which allowed us to sort of define the packet steering and packet processing pipelines, with the main focus being reproducibility and providing all of our experiments that we do in our documentation, so the scientific community can not only reproduce them, but build on them and sort of innovate. So our main focus is providing experiments that users can follow and build on, and build the next new shiny thing. And of course, one main aspect we try to focus on is measuring and monitoring on the cluster. So we try to provide as much as observability and controllability on the cluster with SFlow. And SFlow is a network monitoring protocol. This was deployed on our cluster generously by the Nmon folks who have developed SFlow and the HSFlow-D. It's the agent that runs on every single node we have on the cluster. And it collects interface counters, it collects packet samples, drop events from switches, routers, and from every single host node. And this is all aggregated and collected and even dashboard on the cluster using Nmon's dashboards and using Prometheus metric collectors and exporters, where we have everything shown to the users on our publicly available Grafana dashboards. And just to show you a quick screenshot of what this looks like. So this is the Nmon dashboards, and you can see here it lists every single node we have, the traffic going in, going out, throughput, packet drops, TCP flows, and so on and so forth. any metric that you can think of that we can realistically do, it's on there. And another telemetry application we have, as we talked about slightly rushed in the previous slide, is our P4-driven per-packet telemetry. So in some of our switches, we collect every single packet that goes through some of our ports. Those packets are truncated, those are merged, truncated, and we save the packet headers. Those packet headers are encapsulated, so they're sent to Apache Kafka workers where they are stored in databasing where we can query them to look for anomalies, detect anomalies, latencies, look for trends in, for example, jumbo frames and so on and so forth. This is, of course, a system that is modeled after ESNet's high-touch system, which you can go online, find the paper, and read more about it. We tried to build our own in-house system that sort of follows the same model. And like I said, everything is on Grafana. If this is something you're interested in, you can always visit grafana.nrp-nautilus.io. You'll see our publicly available Grafana dashboards. If you're interested in seeing and querying Prometheus and seeing the metrics yourself, we have prometheus.nrp-nautilus.io, and we have Thanos for long queries that go beyond 2 months. We store metrics for 5 years on thanos.nrp-nautilus.io. And thank you all very much. This is our QR code for our website, and I ran over time a little bit. I'm just gonna ask if anybody has any questions.
Super cool, thank you. Joel Yeagley. How are you coping with the sort of paucity of future P4 platforms in the network? Like, there don't seem to be that many emerging at this point.
Yeah, so just looking at the past year, we expected momentum to die out with the P4 language, but it's actually after Intel open sourced everything, we see growing more and more interest at least in the scientific and research community for P4. And with NVIDIA adding P4 support to their Bluefield 3 DPUs, there's certainly growing interest.
Yeah, so if you replace the DPUs with, or I should say the switches with the DPUs, you have yet another heterogeneity to introduce into your test bed, since you presumably won't have the same NIC everywhere. But yeah, I think that is an interesting problem to have, is that you know, you're tied to a limited number of switch platforms.
Yeah, thank you very much. Yeah, we're always trying to add sort of heterogeneous hardware, different variety of hardware, and it's always very interesting to see the problems that introduces. All right.
Thank you very much, Mohammed. If there's no further questions, thank Mohammed. Really enjoyed that insight into some of the challenges you're dealing with in higher ed and research. Thank you very much.
All right. Thank you all. Thank you very much.